you can see another example of an instance of a knapsack problem. So the number of objects given are equal to 5. The capacity of the knapsack is 60. And W1, W2, and so on up to W5, these are the weights of the objects. The given weights are 5, 10, 15, 22, and 25. Also, profits are given P1 to P5, and these are the profits of the objects. Now you have to solve this knapsack problem using greedy approach. So you have to find an optimal solution in the form of a vector for the given knapsack problem. The given problem is a fractional knapsack problem. As I have been discussing in the previous session, that knapsack problems are of two types. If I simply say knapsack problem, then it means that it is fractional knapsack problem, where an item can be filled into the bag fully or partially or no filling at all. You can fill the item fully, that means 1. You can go for fractional filling, or you can go for 0 filling. Whereas another type of knapsack problem is 0-1 knapsack problem, where there will be no availability for fractionally filling the item into the bag. So we'll talk about 0-1 knapsack problem later. For now, we were discussing only fractional knapsack problems and how to solve them using greedy method. I have represented the given problem in the form of a table for the convenience of solving it. So the number of objects are 5, the bag capacity is 60. I've given some numbers to the objects, 1, 2, 3, 4, 5 objects are there. And for each object, the profit and the respective weight I have tabulated. Now, as per the algorithm, the greedy algorithm, we are going to calculate the P by W value for each object. Profit divided by weight value, we have to calculate for each object. This we are calculating because if necessary, we will have to fill the item partially into the bag. So here you can see for object number 1, the profit is 30. And this profit 30 will be earned for 5 kgs of the items, 5 units of the item. Now I'll have to find out if the item is 1 unit, 1 kilo, how much of profit will be earned. So for 30 is the profit for 5 items of object 1. Then for single item, the profit will be 30 by 5, which will be equal to 6. In the same way, you'll calculate profit for object 2. 40 is the profit for 10 items. For single item, the profit will be 40 by 10, which will be equal to 4. As such, I have calculated the P by W values for all the 5 objects. Okay, now we'll start solving the problem. Now the given bag capacity is 60. The bag given is with capacity 60. I'll start filling up these objects into the bag. So the objective function for the given knapsack problem is you have to fill the bag such that maximum profit is earned. That is the objective function. You have to fill the knapsack bag such that a maximum profit is earned. The constraint for the problem is that the knapsack has a capacity, maximum capacity, which is equal to 60. So this is the given constraint. This is the given problem. The objective function is to fill the bag to earn a maximum profit. So we have defined what is the problem. We have defined the constraints. We have defined the objective function. Now we'll start filling up the bag. So as I said, whenever you are going to fill up the bag, you'll always start by choosing an object with the maximum P by W value. Maximum profit by weight value. So you can see that the profit by weight value for object 1 is 6. For object 2, 4. For object 3, it is 3, 3.5 and 3.6. So whenever I have to fill up the knapsack with any one item, I'll choose the item with the maximum P by W value. So I'll start by choosing object 1 to fill it into the bag. Okay, so I'll try to formulate a table. The table consists of 4 columns. What is the job? What is the object that you are considering? What is the object that you are considering? This is not job, but this is the object. Which object you are considering? What is the remaining capacity of the knapsack? I'll call it as CU. After that, you'll have to decide whether you'll add this object to the knapsack or not. You'll partially use it or you'll fully use it. Then what is the updation to the solution vector? So I'll start filling the bag by first choosing the first object whose weight is 5 kilos. So I have started by choosing first object whose weight is 5 kilos. What is the remaining capacity of the knapsack? It is 60 because initially the bag will be empty. So remaining capacity of the knapsack will be equal to M, which is equal to 60. Now, this is the remaining capacity of the bag. This is the weight that I have to fill it into the bag. Can I fill 5 kilos into 60 kilos? Is it possible? Yes, it's possible. So I have decided that object 1 will be added into the bag fully. All 5 kilos, I can fill it into the bag. So if you have decided that you'll fully fill the item into the bag, then in the solution vector, you have to fill a 1. 1 indicates that you are fully filling the item into the bag. Now this solution vector, this 1, you are going to place it into the solution vector at this location. So you can see that there are 5 places in the solution vector. Each place will indicate the status of an object. This is the place which indicates the status of object 1, the status of object 2, this location, the status of object 3, and so on. So for now, I have decided object 1 will be fully filled. So I'll put a 1 at the first location, first place in the solution vector. Now, next step. So I have made a greedy choice here, isn't it? So why I have chosen object 1 in step 1? Because it has highest P by W. So that's a greedy choice. So at each step, among the objects that are available, I'll make a greedy choice. And what is the rule for my greedy choice? I'll choose the object which has largest P by W value. So one is gone, object one is gone. Now you have remaining objects. Remaining objects are 2, 3, 4, 5. Now which one should I choose? I'll have to make a greedy choice. Among the available 4 objects, I'll choose the object with the maximum P by W value. So I have chosen object number 2. And its weight is 10 kilos. Now what is the remaining weight, remaining capacity of the bag? Previously it was 60 kilos. I have filled 5 kilos onto it. I have filled 5 kilos. Out of 60 kilos, I have filled object 1 of 5 kilos. So the remaining capacity will be 55. Can I fill 10 kilos of object 2 into the bag? Yes, it's possible. I can fully take object 2 and fill it into the bag. So I have decided I'll fully fill into the bag. Now at this location, in the second place, I'll put a 1. So now object 1 is fully filled into the bag. Object 2 is also fully filled into the bag. Now, step 3, again make a greedy choice. So I'm going to choose object number 5. Object number 5, whose weight is 25 kilos. The remaining capacity of the bag is 45. Now, among 45 kilos, can I fill 25 kilos? Yes, it's possible. So the item will be fully filled into the bag. Now I have to put a 1 here because the item I'm filling is 5th item. So at 5th location, I'm going to place a 1. Then next step, object 5 is also filled. The remaining items are 3 and 4. I'll choose object 4. The capacity is 22. The weight of object 4 is 22. But the remaining capacity of the bag is only 20. So I cannot fill object 4 entirely into the bag. Partially I can fill. So how much of it I can fill? Out of 22 kilos, I can take only 20 kilos and put it into the bag. So here you can see that there is a fraction 20 out of 22. Only that much of object 4, I can fill it into the bag. Now here at 4th location in the solution vector, I'll fill it up with the fraction 20 by 22, which indicates that object 4 is partially filled into the bag. Now, there is 4th item is also gone. It's partially filled into the bag. Now, only remaining item is 3. Now, 3rd item, whose weight is 15, but I cannot fill it into the bag because the bag is fully filled. All 60 kilos of items I have filled into the bag. So no empty spaces left out into the bag. So I cannot fill object 3 into the bag. So it's a 0. I cannot fill object 3 into the bag, indicated by a 0 value in the solution vector. This is how, given a fractional knapsack problem, you'll solve it by using greedy approach. Now I'll have to calculate whether the greedy approach that I have used, it has to satisfy the constraints. It should give me the maximum profit. Okay, so this is the solution vector that I have got: 1, 1, 0, 20, 22, 1. So I have got this solution vector: 1, 1, 0, 20 by 22 and a 1. Now I'll try to calculate and see how much of weight of items I have kept in the bag, I have filled in the bag. Now I'll try to calculate the sum of weights, right? So for this, I'll start calculating. X1 item, this is X1, the first object, which is fully filled. So that will be 1 into its weight. This will be W1 into X1. Weight of first item is 5 and it is fully filled. So it is 5 into 1. Then second item, W2, weight of second item into whether it is fully filled or partially filled. It is 10 into 1. Then this is W3 into X3. Object 3 is not filled, so its status is 0. Its weight is 15, 15 into 0. So I have calculated the sum of products of weights and the objects. Now I have got which is 60, which is less than or equal to M. The maximum capacity of the bag is M. So the given constraint is satisfied by the solution vector. So the solution vector X that I have produced by applying greedy approach is feasible because the maximum weight constraint of the bag is satisfied. So I have in the previous session defined what is a feasible solution and what is an optimal solution. A feasible solution is a solution which satisfies all the given constraints. So the solution vector that I have produced here is a feasible solution because it is satisfying the constraint. And the constraint is maximum capacity of the bag is 60. Now, there might be many solutions, among which some of them will be feasible solutions. Among feasible solutions, there will be one optimal solution. So I have proved that the solution I have generated here is feasible. Now I'll have to also prove whether it is optimal or not optimal. So for that, I'm going to calculate this part. Sum of products of profits and items. Now, how to calculate this? This is P1, X1, profit item 1 and status of item 1 plus profit of item 2, P2, and its status X2, whether it is fully filled into the bag or partially filled. Then this will be P3, X3, and so on. And I have calculated and I have got a profit of 230. Now, whether it is optimal, because I have applied a greedy choice, I'll assume that the solution X is optimal because profit is maximum. But I'm assuming that it is optimal, but it may not be optimal. It may be less optimal because, as I said in the previous session, greedy choices will make decisions at each step, which are greedy decisions. That means at this particular step, whichever is best choice, I'll take that choice. I'll not explore all the choices. I'll consider myself, I'll restrict myself by making a greedy choice. That is, greedy algorithms always go for locally optimum choices. The choices that are optimal locally for that step only. I'll not bother about what has happened in the previous steps. I'll not bother about what will happen in the future steps. I'll check in this particular step what is optimum and I'll make that greedy choice. So whenever you are making locally optimal choices, they may give you globally optimum solution or they may not give you globally optimum solution. But the assumption in greedy algorithms is that by making locally optimum choices, I will get a globally optimum solution. That is my assumption. So locally optimum solutions may give you globally optimum solutions, or they may not give you globally optimum solutions. Okay, so this is another example that I have discussed for solving knapsack problem using greedy approach. Now I'll try to share with you the algorithm representation. This is the algorithm greedy knapsack, which has a few parameters. N is the number of objects. P is the profits. W is the weights of the objects. M is the maximum size of the knapsack. X is the solution vector that you have to formulate. Now, initially the solution vector will be empty. And Cu, the remaining knapsack capacity. Cu is the remaining capacity of the knapsack. Initially, you have not filled any items into the knapsack. That means entire knapsack is free. So the remaining knapsack capacity will be equal to M. The full bag is available for filling. Now you'll repeat the steps for first object to nth object. And here this loop will repeat where, assuming that all the objects are ordered in non-increasing order. And algorithm representation. So algorithm is the one that you'll be able to execute on your computer. Okay, so for this particular algorithm, I am reordering the objects in non-increasing order. Okay, now I'll assume that all the objects are ordered. Now I'll repeat the greedy approach. This is the greedy choice there. This is the part of the code where you'll make the greedy choice. For each object, from first object to the nth object, you check if the bag is already full. If the bag is already full, you cannot add the item into the bag. So if the bag is already full, you'll stop. Or otherwise, if the bag is empty, then you'll fully fill the item into the bag. There is a 1 here that indicates you're fully filling the item into the bag. And you are going to update the remaining capacity of the bag. This you'll repeat for first item to nth item. If the bag is full, you'll stop and come out. If the bag is empty, then you'll fill the item fully into the bag and update the remaining capacity of the bag. Now, after coming out, the bag may be completely full or the bag may be somewhat empty. That means the last item, you may fill it partially into the bag. Now, this is how you are going to partially fill an item into the bag. An ith object, partially filling is 20 divided by 22. Last example we have calculated 20 divided by 22. The remaining capacity of the bag divided by the total weight of the item, 20 divided by 22. That was the partial fraction. Okay, so as such, you are going to partially fill the last item into the bag. All the items you will fully fill. The last item you will partially fill. The remaining items you will not be able to fill them into the bag because bag is full. So this is your algorithm, greedy algorithm for solving knapsack problem. And the time complexity of this algorithm is big O of n. I've got this n because you can see here x is initialized with 0, constant amount of time. It will be repeated for only one time. This statement, cu is initialized to m. It will also be repeated only for one time. So it is constant amount of time. Then this part, if part, will also be executed or it will not be executed. Again, constant amount of time. So constant amounts of time, I will not bother. Now, this is the loop which will repeat for n times, the variable part of your algorithm. This loop will be repeated for n times. If this loop is repeated for n times, then this statement will be repeated for n times. This statement will be repeated for n times. And these statements may be repeated, may not be repeated. So as such, it will be 3n. Actually, this entire loop, it will be 4n. So again, when you represent the time complexity in asymptotic notations, you'll remove constants. So I'll remove 4, then I'll be left out with big O of n. This is the time complexity of the algorithm. So